All right. So, well, last time, oh, why is today so high? So today we will kind of going into more on programming. Okay. So we will talk about more codes. Later on, you will see more codes, and we will revisit everything that we have talked about from chapter 2.1 all the way down to 2.5. All right. So we will start with this program last time, right? Still remember this program? This program is talking about the pointer, right? The pointer that you are using in the parameter parsing. Okay, so you are parsing the parameter to the prefix, and well, so what happens then? It is because it is within the same process. Okay, so you have to get in your mind that what is the meaning of within the same process? It means that all the memory are in one piece, okay? Although I draw in this way, the two threads are separated, as well, they're actually not. You can reveal the truth in this program that I have toolbox. That toolbox talking about this input variable used to be the value 10. And in this program, you point to that element. Why you're pointing to that element? Because you point to the element that passing in the address, and the thread function receives the address and use the address directly. Okay, so this is where we stopped last time about this program, and I give you a challenge that you go back to home and I don't know. Okay, I know that after that lecture you have 2 midterm exams, right? One is on Monday, another one is today. Okay, so it's kind of unlucky that I guess very few people have tried this. Okay, some of the people already tried this program right in front of the class and then asked me later after I dismissed the class. And this program, I will do it again. All right. So let me close all the things that I used to have, so that you will see the clean environment. All right. So this is the code, example code, chapter 2.6. All right. So this is the code, right? This is the code. And I executed the code in front of the class last time, and everybody gets so puzzled and frustrated about this. Okay, it's equal 2. Okay, wow, this is perfect. Okay, I got 3, 5 this time. Okay, it's supposed to be 1, 2, 3, 4, 5. Okay, I'm not 1, 2, 3, 5. It's 0, 1, 2, 3, 4. Okay, and this time I got 3, 5. Okay, I do it again as if a random number generator. Okay, it gives me 2, 3. Okay, but you shouldn't have this result, right? Because we go through that loop, and this loop should be producing unique number, right? Take a look here. Every time I pass in the I there, okay, and people get frustrated. Why? Because it is a very natural way to write program, right? We pass a number, which is a number I, and the number is actually a variable in your main. Every time I pass in the function, I expect that you will pass different numbers in. But so unluckily, we got something wrong here. Okay, we got something wrong here. So double three shouldn't exist, right? Because you call at different i's. And this time I will tell you about is truth about what is this problem. And the truth is there is something difference between the time you create a thread and the time you execute a thread. Okay, so you have 2 moments. One is the time you create here, okay, and the time you run it. And this is the same concept as processes. Okay, processes, you have fork and execute. Okay, so let's imagine the cases like that. Okay, we call our fork system call, and you create a new process, and then the process start running. It is not always the case that you created and it immediately start, right? You have a guy, this guy is called scheduler. The scheduler will choose whether I should execute the parent or the child, right? This is not you to control. And in threading, we have the same problem, okay? You start this program, and Well, this is not guaranteed that once you start, it will start execute the thread function. Okay? So you create it, you say that, okay, I is equal to 0, I pass down, and you wish that the input carry the pointer value pointing to I, and I is so happen to be 0, and it's not true. It's not true. Okay? So what is going on here in this output? How come we get 2, 3, 3, 4, 5? Okay? Now, first of all, you have 2 and 3. It doesn't matter. It just means that when I start the program, it doesn't run until the I, let's say, I reach the value 2, I got one thread executing. Then I get another thread running, but so happens that the I value is not the time that you say that I want this to be 3. Yeah, it is maybe 4, maybe 5, so and so forth. Okay? And I just change this program a little bit. Okay? The little bit thing is, yeah, I just change the thing here so that you can see the results more clearly. You can see this. You will have the result output 5 because of this. Okay? So do you have any problem about this? This is the time that you execute is not equal to the time, okay, you created. They are of different times. Now, how to solve it? Yeah, you have a problem, right? You have a problem, you should look for a solution. Okay? Last time I tell you to do what? Okay? Last time we have a problem here. We have the problem, we have a problem in pointing the wrong location. I shouldn't say the wrong location, okay? So happen that they point to the same location, in the thread to change it, then it will affect the main. Now, my problem here is, although we have backed up the value from the pointer value, copy back to the local variable inside your thread, but while you're executing, this pointer value here is actually the I is changing. Okay? So the solution is very sad. The solution is not, I will say this, not sexy enough. Okay? We need some little help. The little help is to create more memory. Okay? So the solution is very straightforward. You know that different threads receive the input, and the input so happen to be the same guy. Then you have a problem. Now, what is the solution? The solution is to break this, what we say that is a sharing problem, right? I don't share the I values, okay, but I share another value which is unique to each thread. Unique. See why is it unique? So what is the global variable? The global variable is actually, I cannot go up using this pointer. Okay. So the global variable is just an integer global variable. I set up it with 5 elements, okay? And here I create 5 elements because I will create 5 threads, and each thread will receive its own designated memory, okay? You have a designated memory, that's why when we pass it in, you won't have any problem here. Okay? So see here, I pass threads of a particular item called global I, and that particular item belongs to that thread. Okay? So this is a total different way to tackle it. But I said it's not sexy because what? Because you create more memory. There's one problem. The second problem is, when we go back to a few slides before, okay, several slides before, then we have this picture. The global variable is actually shared. Okay? A shared piece of memory to different threads. Okay? And in my solution, actually I avoid this I don't have solution slides here. Okay? In my solution, I set up different values to pass in here so that I can give in every thread's starting address to have, and that address won't be used by another guy. This is the first point, and actually the second point, I solved another problem together. I don't have any mutual exclusion problem. All right? Any questions? Any questions? No? Okay. Then some more thing about using a prefect control. The prefect control with the exit call. Okay, I said that the exit call is to terminate the thread. Okay, and with the termination, actually we can pass value out to the caller. Okay, the caller can just join to receive back the solution. Let's say this guy is computing something, he gives the solution to you, and you can pass the solution here. I create the memory. Okay, I need to create a memory so that at the other side you can receive the memory. And this is totally valid. Okay, why is it valid? Because this value that I create is a global thing. It's created by malloc, and malloc is, you know, is a share among threads. So this guy created a memory, and the main thread can wield that memory at the same time. Okay? So this is not exciting, right? It's just, oh, parameter parsing. Okay? Now some exciting things comes up. What is that? Thread scheduling. Okay? So we will disclose to you different languages. On different language, we have different ways to tackle threads. Okay? And there are two main families. One family is saying that we support threads. And their name, we call it support. They have a special name. They call it native thread support. Okay? So you can Google for a while, okay? You can find out native thread support everywhere in the internet. And another stuff is not native thread support, it's what we call library-based support. Okay? So what is the native thread support and library-based support? Okay? Let's take a look at the library-based support. Okay, so what a library-based support? The old Unix. Okay, so what's the old Unix? The old Unix means the Unix that you are using in our lab, right? You can SSH to our Unix, the Unix machine. What is the, we have old and we have new, right? The new Unix is this guy. Let me Google it for you. The new Unix is Open Solaris. Yeah, how many of you have heard of Open Solaris? Open Solaris? No? No one cares about this? Okay? Yeah, only one hand is set. Oh, he is not raising it up, okay? So this Open Solaris is new type of Unix, okay? It's Solaris is our old Unix brand name, okay? The open source version of it is Open Solaris, okay? And except that old Unix, what are the other things that are non-native thread? Okay, we have another keyword here. The keyword I point to, I have to do a copy and paste here. Copy. You can point to any Wikipedia page about green threads. So what are the green threads? Take a look. Okay, so it says, whenever you get a green thread support for a specific language, it means that usually that language run on top of a virtual machine. Java virtual machine. Python is actually a virtual machine itself. Ruby also running on a virtual machine. JavaScript also do this. And well, we call it runtime of a virtual machine. And that virtual machine manages all your threads for you. Okay? So what is the meaning? The meaning is there is a shield. Okay, you can touch the operating system by itself. Okay, and one of the language that this green threads you will find is a bunch of things: Java, Python. Okay, Go. I don't expect that Go is using green threads. Haskell, bunch of things you can think of, okay? So what is so special about this so-called green thread, okay? In operating system box, okay? We don't call it green threads, we call it a many-to-one threading model. So what does it mean a many-to-one threading model? In your program, okay, you write your program, you know that, that language, the manual said that we have thread support. So you open a new thread, you create a new thread, and in the programmer point of view, you have different threads. But in the kernel space, the kernels don't know what is thread. Okay, don't know you have created threads. Okay, it uses one policy structure to govern the entire thing that you have. So what is the meaning? The meaning is operating system don't know. It just gives you one CPU share. Okay, one CPU share. And in the reverse of it, okay, we have the one-to-one model. So what is the one-to-one model? the operating system knows the existence of a thread. You, over that language, you call for a thread, you will receive new type of resource inside of the kernel. The kernel knows that you create different threads. C and C++ will behave in this way. Okay, and we call it native thread support. Okay, so what is so special about this? What's so special is very important. Let's take a look at this little diagram. Okay, not a little diagram, I would say that it's just encapsulate a very important concept. But this one concept is that whenever we have green thread support, we have what we call the language virtual machine or language library. That library will control all the threads for you. Let's say I have this pointer here, means that the scheduler chooses you. Okay, the scheduler chooses this guy, and when the scheduler chooses you, it means that the scheduler chooses that process, and that process receives CPU resource. And what happened? These two threads will be only controlled by the process, and the process say that, okay, I receive 10 seconds, not 10 seconds too much, 10 milliseconds. 10 milliseconds of execution, then it shares resource inside this thread. Okay? So they do their own job, okay? And the scheduler don't know about the existence inside the process. You have two threads, three threads, doesn't matter. Okay? Now, what is many-to-many, okay, or one-to-one model? Since the kernel version 2.16 of Linux, no, that's how many years? Around 15 years ago. Okay? So we have what we call a thread-based scheduler. Okay, and also the kernel knows what is a native thread. Then, whenever you create a thread, the kernel knows about your existence. Okay? So that means what? That means while you are doing the programming over the language to create a new thread to the scheduler, it is a process. It is a process. Okay? So it is very interesting that in Linux, there is a call called getTID. Eh? No, this is a Mac, sorry. Yes, that's why we cannot find it. Okay, let's find a Linux machine. Okay, so this is my Office Linux. Okay, so make sure there's a Linux. Okay, there's a Linux. Man getTID. So this call is a call that inside a particular thread you can call for a return value which is of PID type. But look at the description. It's called get thread identification. So what is the meaning? The meaning is, yeah, the scheduler or the kernel is doing naughty job. Okay, it actually gives you a process PID to your thread, but don't tell you that it is a process. Okay, so it's hide something. If you create a thread to the kernel, it is creating a PID, and it is a process. And what is the good or the bad? Yeah, we have two models. Okay, the good or the bad for the native thread support. Native support is actually the merit for this guy is the reverse. It's the drawbacks on the other model. So let's look at this model only. When you call for, let's say, inside a particular thread, you try to, let's say, you sleep. Okay. Then this blocking call, sleep is a blocking call, right? You sleep for some while. Actually, you just only affect your own thread. Okay, but in the other way round, okay, you call for sleep. Actually, the sleep is to sleep the entire process. And in this model, okay, you have a big trouble. You have a big trouble. You are actually launching a sleep call here. You sleep the entire process. And in our Mac as well as Linux model, we all implemented this one-to-one model. And this one-to-one model won't let this happen. You sleep, then you will only sleep that thread. Okay? So this is the good about the native thread support. Okay? So any question you want to ask about this? Yeah, this is what we call native thread. Okay? And you can queue it for a while. Okay? Let's say iOS. Do you make iOS native thread or library-based thread? Yeah. Google for a while, okay? Android, I'm sure that it is a native thread support, okay? Yeah, because Android is one native Linux, right? And it's a kernel version. What is our kernel version? I don't have an Android phone, okay? If you have an Android phone, you can go to about your phone, and you can query your kernel version. If your kernel version is at least 2.6, okay, then you will receive native thread support. Okay. For iOS, again, this is the native thread support. All right. So this is very important, okay, for you to know about this model. Okay. Then what is the next thing that coming up? The next thing coming up is something that you are very afraid of, okay? The IPC, okay? Inter-process communication. Yeah, someone's IPC, okay? Yeah, so IPC, what is IPC, right? The IPC here is not IPC, it's inter-thread communication. It's IPC, okay? So the IPC model here is just still the same thing that you encounter in process-based support, but it's a lot easier for you to write the program. Okay? So in here, the same model, again, we have here. Let's say we allow you to create a semaphore. Yeah, still remember a semaphore. Yeah. If I allow you to say, oh, you create a semaphore, then the native thread support or non-native support doesn't matter. Okay? You just think of it, oh, I'm writing thread. And the thread memory sharing model allows you to put anything in the memory zone and the global memory zone, just as shown you before. And here, you should put all your semaphore or shared memory in the memory zone and global. Okay? Remember to do this. Okay? Let's say you put your semaphore inside local variable. It doesn't make any sense, right? It is not automatically shared with another thread. Of course, you can do some tricks so that it's shared. All right, so let's see a program. I give you 1 to 2 minutes. I don't execute yet. You tell me what it is. You tell me what it is. Okay? So the program here, you miss some of the keyword. The keyword is in the previous page. Okay? So I just go to the code so that you will start to understand what it's doing. Okay? So the line 2, what is line 2? Actually, the line 2 is a call. Well, when you read it, you understand what it is. Pthread, you skip it, okay? You skip Pthread, it means Mutux lock. You lock the Mutux. Find the semaphore, lock it. So that means that it is from semaphore value 1 to 0. Okay? And you've got the Mutux unlocked. Okay? So, what is this program is doing? I give you 2 minutes to discuss with your neighbor. Tell me what it is. Tell me what it is. Okay? And some variable that you don't know where it is, this is a shared variable. Okay? I put it in a shared object area, maybe it's a global variable or malloc zone. Okay? Please, if you have a laptop, you can download my code and execute this code. We call it Pthread underscore Mutux. It is this code. Pthread. This guy. Okay. So you don't need to know about is a thing here because I extend this code to a long code. The short version of the code is this guy. What this guy is doing? Yeah. You can execute the code for a while and tell me. Yeah, the maximum is you can assume that the maximum is trending, okay? The maximum is trending. And the shared object start with a value 0. Yeah, I see someone is looking at your monitor. Okay, hope that you are really executing and not going to Facebook. What this code is doing? Yeah, you have to understand I will put it in the final exam. Yeah, if it's in the final exam, you are lucky. Yeah, it is an easy question. Okay? Any problem here? What this code is doing? Yeah, are you executing? execute the code, I see somebody looking at the monitor. There's some spy faces, okay? Anybody executing? No? Okay, yeah, execute the code, no. Okay? Becky, you know what that? Don't know, okay? So, anyone here? No, we don't know. Yeah. How about you do? Are you executing the code? No. What? Yes, you don't understand. Okay? So let me explain to you. Very easy, right? You get a while loop and this is a thread function. Okay? So every thread, assume that we have many threads executing this same code. Okay? And every time when you try to execute something, okay, you have a mutex lock and mutex unlock pair. Right? So as if you are decrementing the semaphore value using the lock and changing the semaphore value from a lock to unlock using the unlock call. Okay, so there's a lock, there's a unlock, and in between of that, you will change the share object to some value. Let's say increment by 1. Okay, let's say there's only one thread executing it. Then what will happen is as in a stupid loop, right? A stupid loop changing the share objects only 1 and then 2 and then 3 until you reach the maximum. But how about with multiple threads? If you have multiple threads, then this program starts to get some fun, okay? This lock, okay, is like a semaphore lock, right? Whenever you have a semaphore and it's a binary semaphore, then it says we are protecting some code, okay, and allows the only one process to go in. All right. So let me execute the code, and the code is start with something here. So the random, we set up the random, and I will also ask you for something more. Okay. So the Pthread Mutux code. Okay, so I will ask you for two inputs. I changed the program so that you can use the command line to control how many threads you want to create, as well as what is the maximum value that you want to attain. Okay, so let's say we create 4 threads. Okay, and the value that you want to attain is 20. Okay, so what will the result be? I will print out something. Eh? Oh, sorry, I swapped the numbers. Yeah, it's the maximum value and 4 threads, okay? Maximum 20, 4 threads. So it will execute it. I just print out per thread, it will print out a share value that you receive, okay? So what is the result here? Maybe 20 is too much, right? Maybe I play with 2 threads only, and the maximum value is 10. Okay, so do it again. Can you see any 2 threads output have duplicated value? Is there any duplication? No, no duplication. So that means as if, okay. The Mutux lock working. It's working, right? It works by protecting this share variable in a mutually exclusive manner. Okay, and I choose it to go to sleep for a random number of time. So the random call here, where is the thread function? Okay, so the thread function, I will choose, half of the chance you will sleep for 1 second, half of the chance that you will sleep for 0 seconds. Sleep 0 means you don't sleep, right? All right, let's go with some horrible demonstration. How about I choose to have 100 threads. Go up to 500, maybe too long. Maybe 200. Okay. Is it? Oh yeah. Sorry. I always swap it. What happened to me today? Okay. 200, but 100 threads. I want to launch 100 threads in my program. Okay. What will happen? Yeah, then they will say that, oh, I'm responsible for 3 of the updates, 2 of the updates. Some poor guy will only have 1 update. Any guys with 0 updates? No. Yeah? Then Seems not possible. Why somebody get 4 updates? Somebody 6 update? But only go to 200. Seems to be impossible. Huh? Let's try something outrageous. 200 threads, 10. Eh? Did I swap the numbers? What happened today? There are 10 numbers, okay, 200 threads. So somewhere we put 0, okay? And now let me try some outrageous number. 500 threads. No problem, huh? I got a MacBook Pro, huh? Yeah, you are using Windows, sucks. Yeah, no problem, yeah. Wait. Now, what if I go to another operating system? Okay? So I need to have a SSH. Did I terminate my SSH. Sorry. Let me have SSH, and then I shouldn't terminate it. Okay. So let me check for a while. I forgot what is the number of the architecture of my Linux. 64 bits. I want to have a 32-bit system. Do you know where I can find a 32-bit system? Linux what? Linux 2? Right, 32-bit system here. Okay? So I go to TAM and create code.c. Okay? So Control A, Control C. Sorry. All right. What? Code.c -L Pthread. Good. Compilation finished. So this is Linux 32-bit. I want to create the maximum value go to 200, maybe 300. I have a number of threads, 1,000. Now try again. How about my 64-bit system? Where is it? Do that. What is the input? I already remember. Oh wait, 300, 1,000. Okay, let's go. Mac is more. How can I describe it in English? More doable. Okay, more doable. Yeah. So, later on, when we go to the memory, okay, we'll explain to you why. It is purely because of I'm running out of the memory. Okay. So the calculation is like this in a 32-bit system. 32-bit system calculation is I have 3 GB, 30. How to calculate it? Yeah. Well. Okay, so there's a 3 GB space, and every thread will take 8 meg. So approximately 384 threads I can create on a 32-bit system. Okay, so let's try. What is the number? I always forgot. Oh, okay. Let's say I create 350. Oh, already go beyond the limit. 300. What? Linux sucks. 250. What? 1 year. What happened? 100 is okay. Eh? What happened? Hey, who is executing? But shouldn't be any problem. Why? Tell me why. Not possible, huh? I don't know. Okay. I don't know why. Why is that? Fortunately they are gone. Huh? Why 80 is resource temporary unavailable? Let me check here. You limit. Maybe someone changed this. U limits. What? What? U limit. Stack size. It's still okay. What happened? Let me try again. 300. 300. I can't explain. I don't know why. Don't ask me yet. Okay. Let me go home and do some investigation. Why is that? Too few. 10 thread, no problem. Oh, I know why. Let me see. Oh, I remember why, okay? Now, the reason is, I can explain to you, and it's because of you guys, okay? System of me tell me that they know that someone knows football. then he tell me that he will limit the number of processes that every user can create. And I run it on Linux. Linux is using native thread. Native thread means that each thread is equal to a process. So I'm BJ. I cannot check because it's in a system of inside using the /etc/security config. If you want to know that there is a there's no way to have, but I can use virtual machine. There is a security process. Yeah, there's a limit config I cannot change. Okay, don't worry. Yeah, what we have is a MacBook. Okay, a MacBook is powerful enough to run something, right? I have Ubuntu. Yeah, wait for a moment. Okay. You believe in a MacBook, you should put up in 10 seconds. I give you. Okay. Why? Hey. Yeah, good. Okay. Oh, this is 64 bits. Okay. I let me do this during the break, okay? Because I've had a virtual box as well, and I have a 30-bit here. But virtual box takes some time to put up, okay? So let me put it up first, and let's continue about this program. This program, you know it. Now you understand it is mutual exclusion setup, okay? So you can create different threads and control its access, okay, by using the Mutux lock and Mutux lock. Very beautiful call. You don't need to take any control. You don't need to set up, this is binary semaphore, you create a semaphore, and down and up. No, they translate it into lock and unlock. Very beautiful call, but how to create that guy? Okay, so just go back one slide. To create that guy, we have two ways. One is during the time you initialize, you create a variable, you declare that there is a Mutux, and you call it Mutux. You can initialize it with sub-initializer. But let's say you are not doing the creation like this. You're not doing creation like this. Then here will be another method for you to initialize it. To initialize it into the unlock state. Unlock state. Whenever you initialize it to unlock, then you just lock it and unlock it, so on and so forth. Okay, this VirtualBox is irritating. Yeah, I know you're ready. Okay. What? Okay, actually it's not put up. All right, so this is the Mutux, and another guy is very horrible guy. Okay, so I know that this morning you got a midterm. Okay, I shouldn't teach this horrible guy now, but I know I don't have too much time in this course. Okay, so I cannot wait, but I have to say it now. If you are very uncomfortable with it, okay, go down 2 floors down and you'll get coffee there. Okay, you'll buy some coffee and take it. And what is this model? This model is still what we call a producer consumer model, but in our prefab programming paradigm, it is a shame that there is no counting semaphore. They don't allow you to have semaphore. Okay? Although you can find some other things like not Pthread, semaphore.h. Yeah, you can find semaphore.h. And it seems that you can include the semaphore.h, but I want you to keep your warning. This semaphore.h is not portable to all systems. They are not in the postfix standard. Okay? So that means it's non-standardized base. It's from what we call open group things. Okay? And if you really want to use it, okay, take your own risk. And in this model here inside the Pthread, we don't have semaphore control, so I teach you another model. And this model is used by Java as well. We call it monitor model. Monitor model. Okay, so the name is monitor process synchronization. Okay, so it's called the monitor model. And this monitor model is supported by Java and Pthread. And what is the monitor model? The monitor model is doing something like this. Okay? You set up something, okay? And then we call it a condition. Okay? In Java, they use another method, okay? And that's why I don't talk about Java yet. I talk about Pthread first. You create some condition variable, and the condition variable better given a very descriptive name. Okay, I will call this descriptive name, let's say I would call now. I give some name. One is called full, one is called empty. Yeah, this is the same thing for the Pthread model. Okay, and empty condition means that if I am a producer, I don't obey or I don't rely on the empty condition. You know what? Whenever producer finds something empty, okay, they should not be blocked, okay? So they won't listen to the empty condition. Rather, the consumer listens to the empty condition. The listen means that I will check whether this guy, the share offer, is empty or not, right? Back to this consumer model, and consumer find that it is empty. So what should you do? You go to sleep, right? You go to sleep. And what is this condition variable will do? You will say, I am sleeping because of this guy. No. And because of this guy means that if someone in reverse finds this is empty, please let me wake up. Okay? So I will wake up and someone signal me using this condition. Okay? So this is the way to think what this is about. Okay? Now, the reverse thing comes now. The reverse thing is this guy is sleeping, but this guy stopped running. Okay? So when the producer stops running, let me highlight it. We have another operation called signal. Okay? In Java, we call it notify. Okay? To wake him up. Okay? You are waiting on an empty condition. They're just like some spark. Okay? To make this guy do painful and wake up and say, oh, I should wake up. Okay? And this is what we call the condition model. You wait for some condition and someone notify you through that condition. Okay? And in reverse, we will have the full condition. I try to enqueue, but I find no space. I'm a producer. So I will say that, please, someone notify me or signal me going through this full condition. Okay? And in Java, we call it wait. We wait for some condition to happen, and another guy notify me. In Pthread, okay, we have, I will wait on a particular condition, and someone please signal me. Okay? And I will jump ahead, go to the code first. Okay? In setting up the code, I can give you the real code. The real code is in here, and it is not easy to read. So let's take a look at the high-level description first. We will first log something. Why we have to log something? Because later on we have to check the status of our offer. if the buffer is full or empty, I shouldn't let another guy to touch the buffer, right? Because I'm touching it. Okay, so I will set up the lock here first. Okay, while I'm locking, then I can check whether the buffer is full or the buffer is empty. Okay, when the buffer is full, then I will say that, okay, I will wait over this full. Okay, this is something that you don't understand. I will explain later. Okay, this is very important. So remind me to explain to you. Okay, this full is the thing that I wait for. While I'm waiting, someone, let's say this guy, okay, start executing. And let's say I don't know why it go through this lock. Okay, this is something that I will explain. And I find that now because previously it's full, so it won't be empty. So I will skip this 2 and 3, and then it is full. Because this is full, so that I will signal this guy to say that, hey, wake up, because you are sleeping because of this full. Okay? And continue to execute and EQ and unlock. Okay? So what this Mutux is working in this whole code, I said it's very important. Okay? The library designer is a genius. Okay? How genius is? He put the Mutux here because of what? Because we all know that you are protecting something, and then you want to go to sleep. Now, should you bring this lock together with your sleeping status, and you go to the bed with the lock, like the previous case that I said that you are hiding inside the toilet and sleep with the door locked, yeah, you can do it, okay? You shouldn't do it. So, the designer of this API is very clever. It will ask you to put down the Mutux lock here, so that when you call for a wait, you will together unlock. Okay? You will go to sleep and unlock together, so that this consumer can enter this critical section. Okay? And another way around, let's say this guy tried to notify him, and the beautifulness of this API comes again. You wake him up using this full. This guy wake up, and it won't wake up. Why? Because it should not wake up, because you take the Mutux, and this guy don't have the Mutux, you should go to sleep. So, in the entire API design, when someone tries to signal me, I want to wake up, this Mutux will try to get the lock, okay, get the lock of the Mutux. You will fail. You will fail, because I am inside here. Okay? So this is the design of the API. Okay? And the whole working is like this. Then we will try to go to read some of the code, the producer consumer code. Okay? So this is the whole code. Maybe I zoom out a bit. So let's take a look at the producer. The producer is very easy to understand. Easy means that I give all the comments here. You should read the comment as well. Is this full? Yeah, it is full. Then I will wait for the get a signal by the consumer. If it is empty, that means that I should signal my counterpart. Then you will do the producing, add something to the buffer, okay, so and so forth. Now let's take a look at the working. Yeah, why is it getting so hot? Huh? This room sucks. Huh? All right, producer, consumer. Let's go. So I'm yeah. Oh yeah, it's flowing. Okay. I just make a beautiful drawing. Okay. Yeah, it's beautiful. For a guy who always feels it's art subject, it's very beautiful. So this guy is a consumer, this guy is producer. The producer keep producing something. Let me suspend the process so that you can see clearly. Suspend. Okay. So this guy produced R. It so happened very hard to see. Maybe the last row. Okay. This guy produced W, and this guy cannot take a consumption because I'm running. Okay. And whenever you have a producer, consumer gets me the items out, the producer cannot run. Okay? So this is the whole thing. But what? the coding itself contains so many cores here. Okay, so in this course, okay, first of all, I'm lazy. Okay, I don't want to set up assignment. Okay, over this. Do you know why I don't want to set up assignment? Because there's so many randomness here. Very hard for me to correct your assignment. Okay, not for me, for Kelvin. Okay, Kelvin will quit this job. Okay, if I say, oh, you go to mark a dining philosopher code. Okay, yeah, then he won't do this job. Okay, then if you want to code things like this, you have to follow this model. But I don't ask you to code anything. Okay, and if you really want to try out all the classic models that I talked about, dining philosopher, producer consumer, as well as reader-writer problem, but you don't want to use the condition and the signal. Actually, you can create your own set of semaphore data type using the condition statement. Now, what is it? Let's take a look. The down call, I create a down call. Okay, the down call I create is like this. I create a Mutux. Okay, why there is a Mutux creation here? Because the semaphore data type that I create has three guys. One of the guy is value. Whenever you try to check the value, you should protect it by using a Mutux. Okay, so I set up Mutux. If the value is 0, then I will wait. Yeah, is it something similar? No one knows what I'm talking about, right? I know. I know no one knows what I'm talking about. So let's check again the course homepage. IPC, where are you? Okay. So it's very, very long lecture. Oh, we missed it. Okay, so the down illustration. Okay, take a look here. The down illustration. While the value is 0, you will have some special sleep. Okay, now let's take a look back to this code. While it is 0, this is a special sleep. Okay, I just do a 1-1 mapping. If you can go past this while loop checking, you can decrement the value. Now let's take a look back to the design here. When you go past this while loop, you can decrement the value. And we enable the interrupt. And what is the we enable the interrupt? You unlock the Mutux, so that other people can get their Mutux lock again. Okay? So this is my implementation of the semaphore using the Mutux lock and conditional waits. Okay? So again, there's some challenge for you. You can use this to implement any semaphore-related algorithm. Okay, you can find some semaphore-related algorithm in the net using the semaphore library that I create here. All right. So I think I've stopped for a while, and after I have the break. Okay, we will talk about the fast safety. So what is fast safety? Fast safety doesn't mean anything about the safetiness about your computer, okay, but about the library call. What? You tell me I didn't start the recording?